Okay, it's 11 a.m. Good morning, good afternoon, everyone. My name is Cherry Kubota at the Ohio State University. I'm the host of this Indoor Ag Science Cafe. We have been doing this since 2018, so it's quite a bit of time. Initially, we were focusing on indoor vertical farm technologies. And now we expanded with two additional organizations or group of researchers. So including greenhouse and basically all kinds of systems to grow plants under some levels of controlled environment. So I really welcome you, particularly if you are the first, participant, first time participating in this effort. So we are doing this monthly, Tuesdays, usually 11 a.m. Eastern Time, US. All right, so wanted to show upcoming schedule. Today we have special speaker from Switzerland. And I'm going to read the title and the name in a minute. But next month, we have from US Resource Innovation Institute, Derek Smith, who is the executive director of the institute, talking about his programs and accomplishments and impact. It's quite impressive organization. So if you're not familiar with, this is the opportunity to learn what they are doing. The second one in the list, April 29th, marketing CEA herbs. So this was suggested by CEA herbs group, Dr. Alicia uh, Lin, may not be pronouncing right, but University of Tennessee. So that's good marketing economic side of talk. And then May, we have a food safety talk, food safety research recap. How do foodborne pathogens survive in NFT and DWC systems? Um, Very famous researcher in this area, Dr. Angela Weller from Texas Tech University, is talking about that. June Cafe is currently open, and then I welcome your suggestions, recommendations. So if you have desired presenter, come to this, platform. Um, Let me know, and then I will approach and then find out if that person can talk. You can also, nominate yourself. That's fine with us. What we are doing is basically sharing information, science-based information. Could be a private side or could be academic side. So basically learning what's going on and what is behind the technology. So today's talk is going to be given by Dr. Jonas Roch from Voltiris. Do I pronounce right your company?
That was perfect.
Okay, great. And then the title, thank you. The title of this presentation is a Spectrally Selective Solar Panels for Greenhouses, a win-win dual land use opportunity for more profitable, sustainable, independent greenhouses. So this is an excellent talk. I want to add one more thing, Jonas, before you take over. So heat management in greenhouse is really important, particularly in North America, including Mexico, because we have an extreme heat and humidity, right? But not many technologies can mitigate that. So keep that in mind, Yes, European technologies, usually driven by Dutch, but not so much heat management because they don't have that extreme heat like we do. So, all right, so that's good introduction to have Jonas connecting from I don't know where you are in Switzerland.
Actually, at the moment, I'm in Canary Islands, so in Spain, but I'm
Oh,
usually in Switzerland.
okay, okay. Canary Island sounds good.
Yes, yes. And thanks for the introduction, Thierry. And also thanks for telling me about the specific context in the US and Mexico. Actually, the heat reduction is one of our focus because that's one also of the outcome, agronomical outcome of our solar panels. And I'm looking forward to tell you more about our solar modules compatible with greenhouse crops. So I will just try to share my screen. I know it worked before, but so thanks again for the introduction. My name is Jonas. I am the CTO and one of the co-founders of the Swiss company Voltiris. So at Voltiris, we developed solar modules that are compatible with greenhouse crops. So as most of you know, greenhouse crops are particularly sensitive to light, and that's where there is usually a challenge when you try to generate green electricity. So for today, I was thinking to first start a bit with the context. So why do we even try to do solar panels for greenhouses, for instance? Then discuss a bit more about our solution from a technical point of view, how our PV panel works. Then look a bit into our offering to the growers. And then I wanted to show a bit one example of a PV greenhouse. That's a project that we are actually working on that we should be installing in the coming month. So I think we can use it as a case study to show how a photovoltaic greenhouse can actually help the grower lower the energy costs. And then I wanted to discuss a bit about the agronomic results that we have and also some of the power generation results that we have, and discuss, for instance, about the heat reduction. Also, I think it would be nice if you have questions, just ask them. I'm fairly flexible about how we we move towards the slides. Okay, so first, why do we want photovoltaic greenhouses? And I think the main point behind this is about the electrification of greenhouses. And we see that there is quite a revolution in the past years, where we see that, let's say, traditionally, the greenhouse growers were working with a lot of hand workers, a lot of manual labor. And also the growers used to rely mainly on walking through the veggies, looking at them and say, okay, here we need a bit more water, a bit less temperature, and so on. And they had, let's say, an unlimited supply of fossil fuel to basically power their greenhouses. And now in the recent years, we have had a lot of development where we see always more robotized, automated systems that are in the greenhouses. And also we see that there is always a more data-driven approach to growing. This means that now that we have very smart climate computers, we have companies like Source, for instance, that try to really get analytics and help the head growers to really take the decisions. And of course, you also have a shift in better controlling the climate in the greenhouse. And this usually happens thanks to electrified systems that are much more efficient, such as dehumidification, fogging, it can be heat pumps, and so on. And all this shift toward the new greenhouse industry basically requires a lot of electricity. And from what we see that by 2030, all the high-tech greenhouse sector will roughly need about 150 terawatt hours of electricity, which is more or less the same quantity of electricity that's needed today by a country of the size of the Netherlands, so in Europe. So when it comes to sourcing the electricity, the greenhouse growers have usually a few challenges. One of them, of course, is the cost, is that usually electricity is one of the expensive energy sources that we have. Another one is sometimes usually access. Some of the growers might not have a power line that is actually adapted to, for instance, power a heat pump. I mean, we easily talk about heat pumps that have, let's say, that needs around 4 megawatt or 5 megawatt of capacity to power, let's say, a 10-acre greenhouse. And you need to have the availability to have the transformers and so on. So usually, if it's not possible, it's too expensive to build a new power line to get access to this electricity. Also, one of the trends, at least in Europe, is that most of the end consumers actually aim to have more sustainable fruits and vegetables. For instance, you have, well, one specific example, of course, is in Switzerland, where the largest retailers have asked the greenhouse growers to be carbon neutral by 2026. Otherwise, they wouldn't sell their vegetables on the market. So this also pushed the growers to go toward more environmental friendly alternatives to natural gas. And one of the solutions to these problems is solar energy. And we see that there is a big potential because greenhouse surfaces are huge. And this means that there is a lot of potential for solar, especially you try to have crops where you have some sun so that they can grow well. The only challenge, of course, is that you can always find some space, some administrative buildings, some water ponds, but the largest of your surface is the glass of your greenhouse. But if you start covering it with traditional solar cells, obviously you will start to block the light coming in the greenhouse. And there is a bit this rule of thumb that 1% less light is 1% less yield. And that's particularly true for greenhouse crops like tomato, peppers, and so on, which need really a lot of sunlight. Also, one of the challenges can be the light inhomogeneities in the sense that you don't want your crops to grow differently depending on the position of the solar panels. So in this context, at Voltiris, we have developed solar modules that are compatible with greenhouse crops. And they are solar modules that will basically filter sunlight such that the crops receive all the light they need. So in practice, it looks a bit like here on the picture. So it's a bit of a parabolic dish that's made from a spectral filter that would split the light spectrum into parts. So all the light that's needed for photosynthesis goes through the module, and we use all the rest to generate electricity. What's interesting is that we install our module inside the greenhouse, so we don't need to ask for building permits. That can actually take quite some time. And also, since we build it directly on site, this also means that you can use this electricity so-called behind the meter, so you don't need to pay distribution taxes and fees on the electricity. Also, you don't need, for instance, to have grid enlargement because you produce the energy actually where you need it. So in order to get this system where we actually generate energy without creating shading, so we rely mainly on a low concentration photovoltaic system where we basically have our filters that will split the light in two, and we concentrate all the green and the near infrared light onto a small solar cell. And by having this concentration, we ensure that the solar cell, which is, in our case, also black, which cannot really let the light through, thanks to concentration, this part is as small as possible. So we ensure that we don't have much shading on the ground. And then, of course, since we reflect the light onto a solar cell, we basically need to always do it through the whole day. So we have a small solar tracking system that will basically track the sun a bit like a sunflower. And what's interesting from a grower's perspective is that by having such a system, we have a production curve throughout the day that is much flatter, which means that early in the morning, we will start to have to reach the peak power and keep it throughout the day. So here are a few pictures of some of our projects that we have currently. So here, this is a project that we have in Geneva, in Switzerland, where it's about 1,000 square meters of cherry tomatoes. Here, it's another project that we have installed in the northern part of Switzerland. It's with micro leaves, such as basilicum and so on. Here, it's a project that we have, for instance, in Brittany. It's a project that we do together with a cooperative, Prince de Bretagne, that's one of the largest tomato producer in France. And here, for instance, we can see very well the green light that we concentrate onto the solar panels. We can see that the solar panels look all green on the picture. And this is a project that we have in the Italian part of Switzerland. So as you could see on the picture, we install our modules inside the greenhouse. So it's an easy installation. So we just hang them with some V's that we can just put on top of the treadie bar. And then we just add some profiles. These profiles have two functions. One, of course, is to hold the module, but the other function is also to implement a solar tracking system that will allow the module to basically go left, right, and up, down. So it's a two-axis tracking. In terms of greenhouse integration, we've also been working with some of the main actors. So for instance, we worked with Horconex, which is one of the growers, one of the greenhouse builder in the Netherlands, where we tried to implement our solar modules on top of the shading screen. And this actually proves quite beneficial because what's interesting is that the shading screen, you will close it when you may have, for instance, excess radiation. And then when you close it, basically you will start to have some albedo effect where the sunlight will get reflected off the screen and improve the yield of the solar modules. It's also quite interesting from a thermal perspective. It's because our modules, will come back to it later. They reduce the heat load in the greenhouse, so there is less, it's getting less warm in the greenhouse. And then basically you can use your shading screen only when the load taken off by the solar panel is not high enough, and then you can close your screen so you don't lose that much light. So in terms of spectral selectivity, so here you can see the spectrum that you can measure behind our modules. So what you can see is that you have basically, so in gray, the peak in gray is basically the spectrum of the sun. And you can see in colors the part of the spectrum that's transmitted to the crops. So all the difference between the colorful spectrum and the gray spectrum is what we use to generate electricity. So you can see basically that we remove the green part of the spectrum and we use it to generate electricity. And we also use the near infrared, which is actually the main part. So it's really the part that generates the most amount of energy. What's also interesting is that when you think about greenhouses, obviously you also think about light. That's really important that as much light as possible gets in. And having our system that is inside of the greenhouse below the glass is actually quite convenient for that. So if you think, usually the growers would say that in the summer, they have almost an excess of direct sunlight. While in the winter, it's more the opposite, where you don't have much direct sunlight, but you have a lot of diffuse sunlight. So our modules, since they track the sun all year long, so in the summer, they will basically block most of the direct sunlight, and you will have all the little part of diffuse sunlight reach the crops. While in winter, since the modules will be lower, because the sun's also lower, then we will block, I mean, we'll filter out some parts of the direct sunlight, but all the diffuse sunlight can still penetrate in the greenhouse because the modules are more vertical due to the fact that the sun is lower. So basically, we don't really stop the diffuse sunlight. So we have less, let's say, less impact on the average spectrum in the greenhouse in winter than in summer. And this is obviously something that's wished by the growers because they don't want us to remove any sunlight in the winter when you need most of it. So now in terms of offering to growers, so we offer them the solar modules as an energy as a service model. This means that we don't sell the units directly to the grower, so he doesn't buy the modules, but he buys the energy that he consumes. So we do this with long-term energy contracts, and we find financing to finance the project. What's interesting with this model is that it reduces the barrier to adoption so that the growers doesn't need to pay a huge amount of capital once, but he can directly start saving from day one. Also, it goes well with our vision of electrification because we will dimension our projects in such a way that we have the optimal self-consumption, but we can also learn from the different projects and start to install, for instance, a heat pump or well, different equipments, batteries, whatever, to really ensure that the growers can use as much as possible of their energy. Actually, I've seen that there were some questions, but I don't see where I can find them here. Yes, so if I can just go through it from Ed Weinberg, for support to use existing greenhouse supports or add new supports. Yes, so we can use existing greenhouse support. So it's about the question from Ed Weinberg. So yes, we use existing greenhouse support. So we just install them on top of the existing trellis bar, and we usually work on the implementation of the V's, so the structure that will hold our profiles. So this part might change from project to project, but the rest remains the same. And about the second question, since we filter out the red light, the infrared light, this also means that the greenhouse runs cooler in the summer. So this is actually something that I will be presenting afterwards. We have actually quite good results on peppers that we did in the Netherlands. I don't know, Ed, if I answered well your questions.
I think the last one is the energy as a service.
Ah, yes.
Yeah.
Yeah,
Describe
sorry.
in your website or not.
Well, to be honest, our website is not, let's say, the best website that there is available. So we are working on it. But yes, if someone contacts us, usually the way we deal with well, growers that would contact us, we will first do a small pre-feasibility study. And then on the pre-feasibility study, we will study a bit what are the different needs, how many modules we can install, what would be the costs. And then based on that, we will propose different options to the grower. Of course, if the grower wants to buy the whole system, he can, but we will try to find some good solutions. And of course, one of them is the energy as a service. The other one could be, for instance, that we have a third party, like an energy provider, that would come buy the asset and then have a deal directly with the greenhouse grower. So we have basically the three different options. We have quite some flexibility. Uh, but yes, on the website, we don't have much more information, I think. Okay. And so to sum up, so with our model, so basically what we propose to growers is that we help them first increase their energy independence, depending a bit on the locations and the type of heating system they have, can basically help them provide up to 60, actually usually it's more around 50% of their total energy needs. We help them improve the sustainability because we provide them with actually a clean energy supply. And since they can re-save directly from day one, we can help them reducing their energy costs significantly, which help them improve their profitability. And of course, what's quite interesting, and we could test it through different projects, is that we can actually install the modules while in operation, which means that for the grower, it's quite ideal. We can just come and install even if there are already plants in the greenhouse, since we only work in the upper part of the greenhouse. Obviously, it's still easier for us to do it in the winter when it's the operations are shut off, but it's still an option that we can do. So now I wanted to present you a bit a use case from a case study from one grower. So it's a grower in which we will do a project in the coming month. And here, for instance, we can see, I mean, these are Swiss prices, which are actually quite high for electricity. But you can basically see the load curves from the grower. So we can see that he has a quite constant energy need, about 350 megawatt hour for a greenhouse of about 6 acres, 7 acres. So that's his electricity needs. And what this grower sees is that the electricity tariff has been actually growing. So the energy itself, so usually in energy bills, you have two contributions. One part is basically the energy price, and one part is the grid fees. And while the energy price itself is usually going down, what we see is that, at least in most European countries, we see that actually the overall price of the energy goes up because the tariffs are always getting higher. So for instance, in his case, he used to pay about 90,000, well, it's in Swiss francs, but it's more or less one-to-one. So it's about 90,000 US dollars that he was paying per year for his energy. And by 2024, he reaches around 100,000 US dollar per year, which means that's almost a 40% increase that he has seen over the last 4 years. But then when we look a bit at his greenhouse, when we see at his electrical load, so this is 15 minutes data, you can see first, well, there are two things that you can see. The one thing that's quite interesting, especially for solar, is that in the winter, so in January, but also in the November and December, there is almost no need for electricity. So that's why it's in the dark blue. And this is usually due to the fact that the growers, they
I
stop
don't
the
think so.
operation.
There's your scarf.
Okay. Was it a question? Okay.
Ed, your microphone is on, so you need to mute. Thank you.
Okay. Yeah, so what we see is that the grower doesn't need the energy starting end of October, and that's usually because he stops his operation. And
Yeah,
then
hold a second. Yeah, thank you.
so he stops his operations, and then throughout the year, when he's actually operating, when he puts his young plants mid-January, then he will start to have a constant base load. You can see also during the night, but the most of its electricity will come throughout the day. So that's why when you see the peaks here, and that's also what you can see in the hourly load profiles. For instance, here you can clearly see that, for instance, the month like July or August, that he has actually most of his electricity needs during the day. The same in November, October, September. So when we compare it to, so now we looked into building a big project at his greenhouse. So we already had existing photovoltaic system, and then we looked into using actually the largest part of his greenhouse, so the green parts, to install about 1,700 modules on a surface of around 1.7 acre. So using this surface, we can install a project of around 230 kilowatt peak, which will generate roughly about 200 megawatt hour per year in his case. So then when we look a bit at the outcome of the project, so obviously as any solar system will be mainly generating electricity in the summer month. But what's quite interesting is that although the project is quite large, 200 kilowatt peak, in the end, most of the electricity can be self-consumed. So we have about 70% self-consumption, and we see that there is actually little energy that will be fed into the grid. So when we see about the total electricity needs, we see that we have about 40% self-sufficiency rate that we will get from the existing solar installation. So this means that we could still increase and make a bigger project, but then we'll start to have also some times where we'll have more electricity that is sold to the grid, and usually this is not as economical. So that's a bit why we don't. So this is usually why we don't do bigger projects unless we know that we can really self-consume the energy. I just see that there is a question about PPFDs and power losses. I will come back to this when I'm talking about the agronomical part, if that's okay. So now about the roadmap. So Voltiris is, well, we're basically a young company. So we are operating since a bit more than 3 years. And up to now, we had basically a main focus on the agronomy because we realized that if our modules had to have a bad impact on crops, it would be a no-go because growers would just not buy it independently of the energy. So we have always added the focus mainly on the agronomy. So we started quite early in 2022, where we actually did trials on small scales with different crops to really see if there was a go or no-go. And since the results were quite positive, we continued in 2023, where there we installed solar modules in at the University of Wageningen in the Netherlands, where there we checked for wine tomatoes. It was also our first project in a greenhouse with the integration. And there we could really start to focus also on the energy aspect of a single module. And by 2024, so last year, we started developing bigger projects, so with about 1,000 square meters and cherry tomatoes. And the idea was also to start exploring what are the potential benefits of having such a system in a greenhouse. So then we started to look a bit different at the different agronomic benefits, such as the heat, for instance. And now basically the idea for 2025 is really to realize these agronomical gains inside of a commercial greenhouse. So now we will be doing different projects, especially a large scale one with these 2 acres, about 2 acres. And there, the goal is really to see on this project that we really start to realize some agronomical gains. Also, from the energy point of view, while until recently we focused on getting a working system, now we really try to focus on the performance, and that's really the goal. That by next year, that we realize all of the points. So that by the end of 2026, that we have a system that produces exactly how much we want, that we can install in the greenhouse, and that's providing agronomical benefits. So now in terms of agronomics, and I think it will answer some of the questions that we see in the chat. So we did different agronomic studies. So we did trials with both academic institutions, but also with industrials, mainly in Europe though. So in the Netherlands, France, close to Orléans, also in Switzerland. For instance, with the Wageningen University, the Delphi Light Improvement Center, and also Svetmo and Agroscope in Switzerland. And we've been working mainly on the greenhouse vegetables. So for instance, tomatoes, bell peppers, cucumbers, and we also did a few trials with floriculture, although we know that the market is not as large for floriculture, so we kept the focus mainly on the three first ones. And what was quite interesting, although I'll deep dive on the agronomical benefits afterwards, we saw mainly for instance, with tomatoes, that due to the lower temperature, that the tomatoes needed less water. So that was one of the points. With the bell peppers, we could really see that we had a lower plant leaf temperature, which was quite interesting. We saw up to 4 degrees a temperature reduction on the average plant leaf temperature. On cucumbers, actually, we made kind of an interesting discovery that we had less trips below the filters. And in the floriculture, we tried to play a bit with different type of spectrum in the red and far red parts. And by playing with the far reds, we could basically improve the crop morphology. So that was quite an interesting outcome. So before let's start about the yield, because that's usually the most interesting part when it comes to greenhouse growers. And for the yield, we usually put the focus on tomatoes because tomatoes are actually quite good light sensors with an output that's usually quite say linear with the total light integral. So here, for instance, we did measurements at a commercial greenhouse in Switzerland, over 1,000 square meters, and we had our filters on top. And when we saw at the end of the year, basically there was so we had about 4% less crops below our modules, but that was actually quite positive because this 4% can be easily explained by the fact that our modules, they are just about 1,000 square meters in the greenhouse that's 60,000 square meters. So the grower didn't adapt the irrigation, didn't adapt the climate to the perturbation of our modules. So we think that by fine tuning, we can easily overcome this 4% to reach really an even yield or even potentially positive. Because what we saw is that there was additional waste due to our modules, due to the fact that the irrigation was too high below our modules. So we had a bit of split fruit, for instance. Then when we look beyond the yield, we see that there is potential for agronomical benefits due to our system. And one of them, of course, is the lower plant temperature and the less water intake. So there we had data in the Netherlands with about 40 degrees temperature reduction. We see that during the night, if you're a grower that don't have two screens, for instance, the modules actually act somehow as a shading screen, so that can increase the insolation during the starry nights. We could see that by playing with the spectrum, especially with the far red part, we could improve a bit the morphology, which is of course not interesting for someone that does vegetables, but that could be interesting for someone that looks for something specific with flowers, for instance. And then we also saw on cucumbers that we could lower the number of trips. So when it comes to temperature, So for instance, uh, oh, sorry, my screen just got disconnected. Which screen can you see now?
We are not seeing any share the screen. So I think you
Ah,
have to
okay,
start with share.
okay. Ah, yeah, share again. Good. Yeah, sorry, I just got too excited. Um, yeah, so now I think this is good, no? You can see it. Yeah. So here, for instance, these are data that we got on bell pepper. So for instance, what we saw is that we could get yield that are very similar or well, actually in the tolerance. So it's basically the same types of yield on bell peppers that we had below or next to our modules. But when we measure, for instance, the light integral, we actually had a bit higher light use efficiency. That's data that we got in the Netherlands. And also we had actually a main focus on this study, for instance, on the temperature reduction. So that's to your point, Thierry. Here, for instance, you have the temperature that we had in a control compartment without our module. So that's the dark green curve. And you can see in light gray, in light green, you can see the temperature below our module. So that's the plant leaf temperature. And what you can see is that at the middle of the day, we basically reach a saturation point where then we keep a constant temperature, more or less, throughout the day. That's a bit around 4 or 5 degrees lower before it goes down. So it basically shaves the peak in temperature. And this was, for instance, the average temperature in August. So this means that the sunny days we usually have even a larger temperature difference, while when it's a overcast day, we don't have so much difference. And that's of course very interesting for growers because if the temperature goes too high, then you start to have problems with the fruit sets, with the plant stress. And of course, if you inject CO2 and you have all your windows completely open, obviously you lose also all the benefits of the CO2 fertilization. So for instance, here where data on the cucumbers, they date a bit, so we could improve the system since then. So what we've seen basically is that we had a bit of losses on the spring season, but a higher performance in the fall season. So that's in 1 year they do 2 seasons. So we had very similar yields at the end. But what was quite interesting is that they counted the trips below on the sticky cards, and they could see that we had about a threefold reduction of trips below the modules. So in the floriculture, without going too much in the details, also we could see the temperature reduction, and this was inside of a greenhouse with the whitewash, with the coating. So even with the coating, we could still reduce by around 2 degrees the average temperature. So that was quite interesting. The main question for us is that would it be possible that one day solar modules could actually replace the coating? That would be obviously ideal because the coating reduces a lot the yield of our modules. So that's a bit of the problem. Also on young plants, we played with the compactness by playing with different far reds to red ratio. Um, and there you could really see that there was a significant difference in the crops with and without filter. Here was more to the point of the isolation. Since our module is basically an object floating midway in the greenhouse, it can also help prevent too much radiative cooling of the crops. So the crop doesn't lose too much energy, radiating toward the blue sky. And that can be interesting in heat savings for growers, mainly if the grower doesn't have two two layers of screen. Okay, so in terms of energy generation, so our modules are basically about 1 square meter in size. And with this 1 square meter, they manage to provide roughly about 140 watts, so it's about 14% efficiency. This efficiency, we reach it especially due to the fact that the black part of the solar panel, this part, made from silicon, is mainly active in the near infrared, which is the part that we reflect particularly well with our modules, which means that we can leave most of the light to the crops without reducing too much the yield of our modules. So here, for instance, this is well, I just did it for the fun. Here is a simulation of how much energy we could generate if we were to deploy a project in Columbus, in Ohio. So we see that roughly there, if we were to deploy in a greenhouse, we could get roughly 400 kilowatt peak per 2.2 acres. I'm not sure how much is an hectare in acres. And this would mean about 480 megawatt hour per hectare. So this is based on the idea that we can put 3,000 solar modules, and we put usually one solar modules every 3 square meters. So it's about 30% ground coverage that we offer. So when we look at the data that we got on the energy, so once again, so for now we focused mainly on the operational system, and that's mainly this year that we put the whole focus on the energy. So here are some data that we got, for instance, from our pilots in the Netherlands. So what we see is that, as I was presenting before, usually our modules, they have quite large peaks. So when you look in May, for instance, when the sun is the solar day is quite long, we see that we have a generation profile that's actually quite flat. Part of it is due to some thermal impact on our modules, but we still see that we can get around 9.5, 10 hours at peak power during a day in May. And this actually comes from the tracking. So here, for instance, you can see different simulations where you can see the impact of tracking on different months. So in December, of course, having a tracking in east-west doesn't bring so much advantage, but the main interest is that you can retilt your modules in the optimal direction so that you really have the most efficient cross-section to capture the sunlight. So when we look about the data that we got, of course, I mean, to be honest, it was it makes now 1 year that it's running, so we improved a lot the hardware since then, but we managed to generate roughly 62% of the energy that we wanted, and that was actually quite an achievement since it was our first project at large scale in the Netherlands. And I think the main interesting part is that we understood quite well where the efficiency losses came in this project. We saw that mainly we had small losses in optical efficiency, a bit of the ohmic losses, so the design of the solar cell where we concentrate the light, because of course when you concentrate light you need to have different designs than when you don't concentrate it. And then we see that we had quite some improvement that were possible with the cabling. And now, basically, so when we look on our roadmap, so when we're in Delphi, so that was this project I was showing you before, so we're about 62% of energy generation. And now, basically, on our new project, we're about 75%. And the idea is that by this April, that we reach about 90% of the power generation when we compare our model with what we generate in practice. So I'm reaching the end. I think there are a few questions, but of course, I'd like to thank the whole team that we have at Voltiris that works day and night, but still say many days on making our product better. So we have many different people with very strong backgrounds that worked in the energy industry, that also works in the plant industry and so on. And of course, also thank the partners that make all this work possible. And in our partners, we have notably 3M, who is the provider of the diacrylic film that we use in our solar modules. But we also have the CSEM, or for instance, the CSEM, the Agroscope, Delphi, Wageningen, that really help us to ensure that our solution is is as efficient as possible in terms of agronomy and also in terms of power performance. And also we work a lot with greenhouse builders such as Orconex and Richel, and also energy utilities that really support us in better understanding the use case of the energy. And all this brings us to our vision at Voltiris, where we see that the greenhouse is basically a central piece in the electrification of our system, where we install the modules in the greenhouse, and this greenhouse is connected to, for instance, data centers that can heat up the greenhouse, to data storage, to EV charging next to it, but that can also actuate heat pumps, for instance, to prevent using fossil fuels. So I hope you enjoyed the presentation, and I think now it's time for some questions.
Okay. Well, thank you so much, Jonas.